Okay, everyone. Today we're going to look at functions defined as definite integrals, which is an extension of the first fundamental theorem of calculus in the most general form. And let's take a look at that. Well, I'm going to introduce the topic by reviewing this definite integral. Now, in calculus, it is very, very special when we integrate a derivative, right? The integral of the rate of change. Using our first fundamental theorem, the integral of a derivative of a function gives back the function. And by the first fundamental theorem, we get f of b minus f of a. So this idea has appeared a lot on the APs when we end up finding the integral of a rate of change. And this is also known as the total change theorem, where the definite integral of a rate of change gives us the total change of that function. On the interval from a to b. And we've done that before. Now, if we take this statement here, and add f of a on each side, we get f of a plus the definite integral from a to b of the derivative of f with respect to t is equal to f of b. Now I'm going to flip this equation and write f of b equals f of a plus the definite integral from a to b of the derivative of f of t dt. And notice that this says that the final amount is equal to the initial amount plus the total change, or we could say the definite integral of the rate of change of f or the total change in f on AB. So let's think about that. The final amount is equal to the initial amount plus the total change on f on that interval, which is always the definite integral of the derivative. So what we can do is we can replace b. We could replace b with any amount. So let's call this, okay, I'll change it back to my black pen, f of x is equal to f of a plus the definite integral from a to x, b becomes x, of the derivative of f with respect to t. So let's think about that. The value of f at a given x, as long as x is in the domain of f, is equal to the initial amount plus the total change on f on the interval from a to x. Or we could think of it as the definite integral from a to x of the derivative of f of t dt. This equation is a way to define a function as a definite integral. So it's something that we knew all along, but we're generalizing the first fundamental theorem of calculus. And notice that when we differentiate this, the derivative of f of a is a number, and that's 0. And the derivative of the integral of the derivative gives back the function with the x replacing the t, using the first fundamental theorem of calculus part 2. Because remember, the first fundamental theorem of calculus part 2 says that when we differentiate an integral where the upper limit of integration is x, and whatever that function is, it gives back this function with a t replaced for the x. Well, here we're going to get back the derivative function with the t replaced with the x. So it follows. Now let's see how we could use this idea to define functions. All right, so I wrote 3 simple problems so we get the idea. And just remember that we define the function, and it's very important to remember the formula, that this new function, f of x, is equal to the initial amount plus the integral from the initial amount, this should match, 2x of the derivative of the function with respect to t. So we have to replace t for x when we take the definite integral of the derivative. Let me just make that a little clearer. Oh, erase the whole thing. So that this is x and this is the derivative of f at t. Okay, so remember, this x matches the upper limit, and the lower limit of integration must match this. Okay, so let's see how we could put it together in number 1. So my f of x will be, I could call it y, or I could call it f of x, whatever you like. Let's call it f of x. F of x, which is known as y, is equal to the initial amount, and the initial amount is this. -1 oh no, I'm sorry, this should be 1. Positive 1, right? That was a big mistake. Y of 0 is 1 here. So the initial amount is 1 plus the definite integral from 0, because this is really f of 0, 0 to x of the derivative, which is cosine, but instead of an x, I'll put a t, dt. And that's it. So remember that the initial amount goes here, the time of that initial amount goes here, this upper limit is always x, and the derivative is in the integrand with a t for the x. So let's try the next 2. Copy those down and try them. All right, so for the second one, the answer should be f of x equals the initial amount, which is 3, plus from 0 to x of the derivative t squared dt. And then the final one should be f of x equals the initial amount plus the integral from 0 to x of e to the negative t squared dt. Now, sometimes the initial amount will not be 0, but most of the times the first time is 0. So that's how we write a function using a definite integral. All right, let's take a look at a few AP problems. All right, so this problem is from 2015, and it was the first problem on the AP exam. And it required the use of a calculator. So this was problem number 1 on the AP in 2015. And so here is an example of what we've been talking about. Let's just take a look at it together. The rate at which rainwater flows into a drain pipe is modeled by the function R, where R of T is equal to, and it just tells you cubic feet per hour. T is in hours, and T is between 0 and 8. And then the pipe is partially blocked, allowing water to drain out of the other end of the pipe at the rate modeled by D of T, cubic feet per hour, in the interval from 0 to 8. And there are 30 cubic feet of water at time 0. So here we have to remember that this is the rate at which rainwater flows into the drain pipe. That's R of T. And the rate at which water is drained, okay, so drain out of the pipe at a rate modeled by D of T. And notice that they also give us that there were 30 cubic feet of water at time 0. So these are the things that we should focus in on. These are the things that we have to really look at. Okay, so let's see. Part A. How many cubic feet of rainwater flow into the pipe during the 8-hour interval? Okay, so whenever they ask for the total amount of cubic feet of rainwater, we integrate the rate at which rainwater was flowing into the pipe. So part A would be the definite integral from 0 to 8 of R of T dt. You do not need to rewrite what R of T is. Save that work for the calculator. And the calculator will give us an answer. The answer it comes up with is 76.570. And that's worth 2 points. 1 for the integral and 1 for the answer. And we will put these into the calculator at the end. Okay, part B. Is the amount of water in the pipe increasing or decreasing at time 3? Give a reason for your answer. And it's asking for the amount of water in the pipe is increasing or decreasing. So what we have to do is we have to find R of 3 and we have to find D of 3. R of 3 will give us the rate at which rainwater was flowing in, and D would give us the rate at which water was draining out. And we would compare those two quantities to see which one was greater. Well, it turns out that R of 3 is less than D of 3, so that the amount of water in the pipe is decreasing at time T equals 3 hours. Okay, so we would have to find those quantities on the calculator. And then part C would be, at what time T is the amount of the pipe water in the pipe minimum? Okay, now that is asking for the closed interval test. And it has to be on the closed interval test on a function that represents the amount of water at any time t. So let's think about that. So R of 3 was 5, okay, let's get this down going, 5.086, and D of 3 is 5.4. We have to put those values back in there before we complete the AP. Okay, everyone, thank you. So the amount of water in the pipe at time t in the interval from 0 to 8 is, okay, now we could put down the initial amount, which was 30, that was given 30 cubic feet, is equal to the integral from time 0 to say x of r of t, which represents the total amount of water that flows into the tank, minus the amount of water that was drained out of the tank. The difference of those two would give us the total amount of water in the tank at any time t equals x. So what we have to do is, this is our function, f of x. So what we have to do is we have to get the critical values of f, which means that we set the first derivative to 0. But the first derivative of this expression is 0 plus, and the derivative of an integral gives back the integrand by the first fundamental theorem of calculus part 2. Whatever letter is up here, we replace here. So we have to set to 0 r of x minus d of x and see what times that would equal 0. So when we set that equal to 0, we find that x can be 0 or 3.271658. And we don't round at this point. Now we use our closed interval test, and this is all on the calculator, which I will do for you. 3.271568, and I'll show you how to store this. And then 8, this is the only critical value in the interval, and we're going to substitute that directly into f of x. And I'll do that on the calculator, but the answers we get are 30, 27.964561, and 48.543686. So the answer is the amount of water in the tank in the pipe is minimum at time 3.272. And this is where you have to put 3 places after the decimal point, hours. You could also write t equals 3.271. I prefer this answer because we don't have to think about rounding. So at time equals 3.271, and it did say at what time t. It didn't say how many gallons of water were in the pipe. Okay, and then finally, part D asks us, the pipe can hold 50 cubic feet of water before it starts overflowing. So that's its maximum. For t greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write, but do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. Well, we know that the total amount in the pipe is 30 plus the definite integral from 0 to w, because we're changing the time to w. Let me just make that a little clearer, because it did say to write a function in terms of w, so we have to make that upper limit w, of r of t minus d of t dt. And when that equals 50, then after that is the time w. When we solve this on our calculator, which we can solve, whatever time w is, the pipe will begin to overflow after that time W. And perhaps we'll do that on our calculator as well. So let me take some time and do some of this on the calculator before I end. Okay, so I wanted to show you how we would approach this problem on the graphing calculator. We would go to the home screen, press the home screen, and go to settings. And in the settings, make sure that the document settings are set to float, 8, and radian, and press OK. All right, this is very important, otherwise we won't get the correct answer. Then we go to the calculator menu, we click on that, and we have a clear page. We could do everything in the calculator menu. So what we will do is we're going to define our function. So go to menu, and we hit actions and define. Okay, so now we're going to define R of t. So capital R of t is equal to, and it was 20 sine, so we go to the trig function for sine. And then we had a fraction bar, so we go next to the book and insert that. And it's just t squared divided by 35. And when we press enter, the calculator knows that's R of t. Now we're going to define d of t. So we go to menu, actions, define, and we type in d of t, d of t equals negative 0.04 t up arrow 3. Okay, move to the right to get away from the exponent, plus 0.4 t up arrow, lowercase t, up arrow 2, go to the right, plus 0.96 t. Okay, and press enter, and the calculator knows that that's d of t, the rate at which water was draining out of the pipe and the rate at which water was flowing into it. Now we have to evaluate R of 3 in part B. So we type R of 3, notice that R is in bold, so it knows the function. And again, I have to do approximately equals because I have this in exact mode. So I'll go down, highlight R of 3, press enter, and then press control, enter. And the answer is 5.086678. And that's what I would put down on my paper. D of 3, and then I do control enter, is 5.4. And I would write those values down in part B. Okay. Now, we had to find the critical values for this function by setting R of x minus D of x to equal 0. So we have to solve that. So we go to menu, algebra, and solve. And we type in R of x and go outside the parentheses, minus D of x equals 0. And we're solving for x. And we press enter. And we get these values, but if we scroll to the right here, notice that the only value between 0 and 8 is the 3.2716584. So we're going to highlight that number, write it on your paper, highlight that number, and and copy it. So we copy it, and we write it here, paste it there, and we're going to store it in a variable, control store, which is above the VAR key next to the delete key, A, and press enter. So now my calculator knows every time I have an A, it is that number. But on your paper, you should write A equals 3.2716584. All right. Now, what we have to do is we have to define a new function, f of x, which will represent the total amount of water in the pipe at any time x. So we defined it as Okay, now we go to menu, actions, define, and we define f of x equals the initial amount of water, which was 30, plus the definite integral. So we go to the key next to the book with all those squares, and we pick definite integral. Okay, and we put down 0 to x of r of t minus d of t. So that's, and we don't need to put parentheses because the parentheses will be put into the integrand automatically. D of t, dt. Okay, this is our function. And remember, this is the way we define a function using a definite integral in terms of its derivative, because r of t, the integral of r of t gives us the total amount of rainwater that flowed into the pipe. D of t, the definite integral of d of t gives us the total amount of water that was drained out of the pipe. And to find out the total amount of water in the pipe at any time, we have to subtract the definite integral of the difference. All right, so now we could use our closed double test. We have f, oh, and we press enter, of course. So we have f of 0, and we know that the answer is 30. F of A, which is that horrible decimal there, and we don't round it at that point. And we get 27.964,561. And then finally, F of 8. And it's very important to copy these numbers onto the chart exactly as they appear. And then, of course, the answer is that the amount of water in the pipe is at minimum at time, and that time would be A. And if we round it off to 3 decimal places, 3.271 minutes. Okay, now let's move down, and I like to show you this new function. We could solve this function when the pipe will overflow. So we go to solve. Algebra, solve. Okay, and we're going to type in the equation. 50 equals 30 plus the definite integral from 0 to w of r of t minus d of t dt. And we're solving here, so we have to go out, so press the right arrow, comma, w. So this, after time w, the pipe will begin to overflow. So when we solve this, and again, we press Control Enter, we should get the time at which, so notice this is negative, but after 50.498 minutes, that's when the pipe will begin to overflow. And that will take care of that problem with the calculator. But they didn't ask us for that, so we didn't have to worry. All right, so I hope that cleared up the calculator piece. Have a great day.